Hey, welcome to the Explainer. Today, we're going to crack open a little mystery that's probably sitting right next to you, that power brick for your phone or your laptop. We're going to uncover the simple but kind of brilliant circuit inside that makes our entire digital world go round.
So it all kicks off with this simple question, right? Why do our sleek, super modern gadgets need these clunky adapters? Well, the answer is that the electricity coming out of your wall is fundamentally different from the electricity your phone actually needs to charge up. They're just not speaking the same language. And to really get what's going on inside that charger, we first have to understand the core problem it was built to solve. We call it the AC to DC problem.
See, on one hand, you've got alternating current, or AC. That's what flows out of your wall sockets. You can think of it like a wave, constantly rushing back and forth, changing direction dozens of times every single second. But on the other hand, you have direct current, or DC. That's the juice all our electronics run on. It's more like a steady, calm river, always flowing in just one direction. So you can't just plug a DC device into an AC outlet. That little brick has to act as a translator between the two.
And that whole translation process, it's got a name. It's called rectification. The circuit that pulls off this magic trick is called a rectifier. Its one and only job is to take that chaotic back and forth AC and basically force it to flow in just one direction, turning it into DC.
Now here's the really cool part. This whole absolutely essential process boils down to one incredibly simple, almost elegant little electronic component. It is the secret hero inside every single one of those power bricks.
Let me introduce you to the diode. The best way to think about it is like a one-way street for electricity. It has one very, very strict rule. Current can go through it this way, but it absolutely, positively cannot go back the other way. That one simple property is the key to this entire thing.
So when electricity tries to flow in the correct direction, the one-way gate just swings open. We call this forward bias. But what happens when that current tries to sneak back the other way? Well, the diode goes into a state we call reverse bias, and that gate just slams shut. The flow of current is completely cut off. And that blocking action is the secret sauce here.
Okay, so we have our problem, this AC power, and we have our special tool, the diode. Let's see how we can put that little one-way gate to work and build our very first, most basic rectifier. And here it is, the halfway rectifier. It is, and I'm not kidding, beautiful in its simplicity. We just take one single diode and stick it between our AC power source and whatever it is we want to power. We call that the load. That's it. That's the entire circuit.
So how does this tiny thing work? Well, remember, AC power is always swinging back and forth. During the first half of that wave, when the voltage is positive, it's flowing in the right direction. So the diode says, come on through. It becomes forward biased, and it lets that positive pulse of electricity pass. But then, a split second later, the AC signal swings negative and tries to flow backward. The diode instantly slams the gate shut. It becomes reverse biased, and that entire negative part of the wave just gets blocked. Chopped right off.
And what we're left with after all that chopping and blocking is what we call a pulsating DC signal. I mean, it's not AC anymore because the current never goes backward. It's always positive. But it's also not that smooth, steady DC that our electronics are craving. Instead, it's just this series of positive bumps with these big empty gaps in between.
So we did it. We made a form of DC. Mission accomplished, right? Well, not so fast. Now we have to ask the really important engineering questions. How good is this pulsating DC really? And, how efficient were we in making it?
The first way we grade the quality of our DC is with a metric called the ripple factor. This basically tells us how bumpy or, well, ripply the output is. For a perfect, smooth DC signal from a battery, the ripple factor would be 0. The higher the number, the worse the output.
And for our simple half-wave rectifier, the ripple factor is a, frankly, shocking 1.21. Now, to put that in perspective, any value over 1 means there's actually more of that unwanted ripple junk in the signal than there is useful DC power. So yeah, that is a very, very rough output.
All right, next up on the report card is efficiency. This is a big one. It tells us out of all the AC power we're pulling from the wall, what percentage actually makes it out the other side as useful DC power. Everything else, just wasted.
And this number right here, this is the real killer. The maximum theoretical efficiency is just 40.6%. Think about that for a second. That means for every bit of power you pull from the wall, nearly 60% of it is completely wasted, mostly just turned into heat. And why? because we are literally throwing away the entire negative half of the AC wave.
So when we look at the final report card, the story is pretty clear, right? The half-wave rectifier does the basic job, but its performance is, well, it's not great. The big takeaways are its rock-bottom efficiency and its sky-high ripple factor. That raw output is just not going to work for most electronics by itself.
Okay, so we've got to do better. This bumpy, really inefficient DC isn't going to power your phone. We need to find a way to smooth out those pulses and, fill in those empty gaps. And the solution, once again, is actually really simple. We just add one more component to our circuit, a capacitor. We just hook it up in parallel with our load, and it's going to act like a filter. Or a better way to think about it is like a tiny, super fast charging battery. Okay, so here's the play-by-play. When that first positive pulse comes flying through the diode, the capacitor instantly charges all the way up. Then, as that pulse dies down and the diode shuts off, the capacitor starts to slowly release its stored energy to the load. It fills in that empty gap where the negative wave used to be. And just before it runs out of juice, bam, the next positive pulse comes along and recharges it right back to the top. This charge, discharge, charge, discharge cycle happens over and over, and it dramatically smooths out those bumps.
So with all its flaws, even with the capacitor fix, where does this circuit actually show up in the real world?
Well, because it's so inefficient and has such a high ripple, you're not going to find a half-wave rectifier in most modern power supplies, especially not your phone charger. It's just too wasteful. But it is an absolutely vital teaching tool for anyone learning electronics, and you can still find it in some really low-power gadgets or in a totally different area, demodulating radio signals.
And that really brings us to the final big question. We've seen that this super simple design works, kind of, but it's incredibly wasteful because it throws away half of the power you're paying for. So what if we didn't have to? What's the clever engineering trick that lets us capture both halves of that wave to get a much more efficient, much smoother DC output? Well, we'll get into that next time.